probabilistic domain, and also we will try to understand how the Rayleigh distribution is going to help us in describing what is called as the short term statistics. When we say short term statistics, we talk about the probability of the occurrence of a particular wave height or occurrence of a wave height less than or equal to a certain specific wave height. As I have told you earlier, the probability density will look something like this. This will be your Hi. So when I want to find out what is the probability of wave height less than or equal to say a specific wave height of say 1.5 or 2 meters, h less than or equal to 2 meters, then I can easily look at this curve and then try to obtain what is the probability of wave height less than or equal to a specific value. In this case, in this example, it is 2 meters. So this is particularly helpful in planning of construction and also in order to assess the functionality of certain structures, etc. Now for short term statistics, for describing the short term statistics of a particular location, short term statistics of waves of a particular location, it is good enough you have wave characteristics for spread for about an year. So if you have measured wave characteristics, remember when we record, the standard practice is to record for once in 3 hours, okay. That means in a day you will have 8 records. So if you are looking for describing the wave climate for a given location, it is good enough to have just 1 year record. That will give you a clear indication of the variation of wave climate. So now let us look at this problem wherein the range of wave heights and the number of waves that has been observed in this each of these class are given here. Now here, so 0 to 1 meter is less than 1 meter equal to 2800 times number of occurrences, then 1 to 2 meters 3600, then 2 to 3 960, then 3 to 4 480, and then the final one is 160. The question is, plot the wave height histogram along with a theoretical Rayleigh distribution. It can be either Weibull or Rayleigh or any other theoretical distribution which we have already seen, but here in this example I have just considered Rayleigh distribution because that is a distribution which is most frequently adopted for describing the wave climate. So in the first column, see the one which is marked here in red color is the column number, and you have in the first column wave height ranging from 0 to 1 and going all the way to 4 to 5. The class interval is now 1 meter in this case. So what is the mean wave height? Mean of Hi by H, or H is here in this case the mean value will be 0.5, 1.5, etc. for this each of this class interval. The number of occurrences I have reproduced as it is given in the problem. Now percentage of occurrence is quite straightforward. You just have to take the column 3 and then divide it by the sum. So that is going to be 35, 45, 12, etc. as given in the column 4. The last column is the percentage of occurrence per meter of wave height from the record. So that is quite simple because you have to just multiply the percentage of occurrence by the class interval. So in this case, in the present case, the class interval is just 1, so you need not have to do anything. So the same value will repeat here. So, I have also indicated, I have also mentioned here about how this column 5 is obtained. Now, having got this, so we have 0.5, 1.5, 2.5, 3.5 and 4.5. The number of occurrences are 2800, 3600, 960, 480, then finally 180. So, these are the values. Now, I will also write the last column, which is 35, 45, 12, 6 and 2. So, we need to first find out the HRMS value, because we can either represent your you can represent the Rayleigh distribution as either a function of HRMS or H mean. So, here HRMS can be easily determined by the formula HI square into frequency of occurrence divided by the summation. So, here HI, I am taking the mean value is 0.5 and the number of occurrences is 2800. The next one was 1.5 and the corresponding value number of occurrences are given here. Use that and divide by the total sum, and that is going to be your HRMS square. So, HRMS in this case is 1.73 meters. Is that clear? So, this is just a basic statistics. Only thing is, after doing the calculations, you need to understand why and where all this information are necessary. So, the expression for the Rayleigh distribution is already given here. So, here it is 2HI divided by HRMS square into exponential of HI negative of HI square divided by HRMS square. So, I can find out the probability of occurrence of wave height equal to 0.5, then 1.5, 2.5 etc. So, this is a sample calculation done for HI equal to 0.5. So, substitute here it will have, you will have the same HI and here also you will have the HI, and then you have your HRMS square, which is 2.99. So, that is going to be around equal to 0.307, which is going to be about 31%. So, in the similar way you calculate for the probability of wave height equal to 1.5 meters, 2 meters, 2.5 meters etc., and these values are provided here in the same way as we have done for the probability of H equal to 0.5. Okay. What is the total probability? So, when I plot this, when I plot 0.5, 1 etc., and then 1.5 etc., then I get a curve like this, and this is nothing but the probability density function. So, we all know that when you integrate this is called as the cumulative probability density function, that is, of course, it has to be equal to 1. So, what we do is we take the area from H equal to 0.5 to HI is equal to 4.5. So, that is somewhere here we are leaving this, note that we are leaving this area. So, from here all the way down to 4.5, then we get, you use the Simpson's rule. I do not want to go into the details of the Simpson's rule, but here it is shown how the Simpson's rule is working out, that is first ordinate plus last ordinate plus 2 into the odd ordinate, then plus 4 into the even ordinate. So, you have to find out the odd and even ordinate within the summation area, and H is the delta class interval. Is that clear? Do you have any doubts? So, this is the basic mathematics. So once you do that, that is going to be 0.923. So what we have done basically is we have taken only up to this area, but we have to also consider this area, that is this particular area, and that is going to be just half into 0.5 into the probability of 0.5, which we have estimated earlier, that is going to be 0.307. So the total value will be this much, and this plus this should be equal to 1. So that thus the total area equal to 1, that is the total area under the probability density curve. So we can plot all these values as we have got these values here. So for 0.5, 0.1, 0.5 earlier slide, then 1.5, all these values. So I can plot these values here, in which, and also use this. So these values we have already got, this is nothing but your observed probability values, okay, that is for the measured data or the observed data, we have got the probability density. Now from this what did we determine? We determined the HRMS, which is going to control the variation of your probability density curve, and once we have done that, we calculated for each of these value using the theoretical probability density. So we have the observed and we have the theoretical, and then we are now superposing. So the blue one shows the Rayleigh distribution, that is the theoretical Rayleigh distribution, and the red one shows the observed probability density. So you see that the values are more or less satisfying, that is, this shows that the wave height as per these observations follow closely the Rayleigh distribution. So I will not go into the details of other kinds of fitting, etc. I am just demonstrating how these examples can be adopted and how the application of this Rayleigh distribution. Now you see that once you, for example, you know that of say east coast, a certain part of the east coast of India follows the Rayleigh distribution. Say for example of Visakhapatnam, where you have a major harbour. So say that it has been proved that the wave heights follow Rayleigh distribution. I can simply say that once if someone has is able to say that of Vizag or any coast for that matter, it follows a Rayleigh distribution throughout the year, and for month January the HRMS is 1.25, then for the month of June it is 1.75, for August it is around 1.8, etc. Then for each month I can simply rely on the Rayleigh distribution, which is so easy for me to calculate because it is a simple equation where you can just use the HRMS value and obtain the probability of any kind of a wave height. How this is useful? For example, I have to carry out a specific operations. I want to mobilize and demobilize offshore in order to carry out some offshore operations. I have to mobilize and demobilize materials. Then this has to be transported by maybe some barges or maybe some vessels. All these vessels will be having certain limiting wave height up to which it can really move around without much of problem. Say assume that a vessel has a limiting wave height, I mean the wave height, if a vessel can operate only if the wave height is less than 1.5 meters. And offshore operations, it is very difficult, very expensive. Once you mobilize, for mobilizing or even demobilizing, it is very expensive. So a proper planning is needed. Now he has a vessel, you have a vessel which has a operating limit that it cannot work when the environment has a wave height greater than 1.5 meters. Then I can easily carry out an analysis based on this, and if I am lucky and if I am having someone who has proved that the wave height wave characteristics follow a Rayleigh distribution, I need to just have a calculator and with the HRMS value or with the wave height mean wave height value, I can easily get the Rayleigh distribution and obtain what is the probability of wave height less than or equal to 1.5 meters in the month of January, in the month of February, in the month of March, etc. So I can draw the monthly probability distribution for that location. What do you get out of that? Once you do that, you can get, well, you can, this helps you in planning. For example, if there is one particular month where the wave climate is going to be very severe, for example in the month of May, and you have a probability of wave height less than or equal to 1.5 is say around 40%, then you have to take care of the risk involved in that within that 60%. So whether is it worthwhile taking that risk, all these kind of information is helpful in the planning stage. And also we have to work out what is called as a weather window. What is meant by weather window? If you want to carry out any offshore operations, you have to have a continuous time, because if you have continuously about 6 months, then you will be in a position to carry out the operation. Suppose, because if that particular task needs 6 months, then you have to search for that weather window, because every time you cannot have 2 months, 3 months, 2 months, 3 months, then you are investing a lot of money on mobilizing and demobilizing your machines. So in such way it is very useful, this kind of calculations. Is that clear? Okay. Now what we have seen is the percentage of the probability of wave height less than or equal to a given specific value, and that is what it gives the, that is what is got from a probability density curve. From its definition, HRMS being average over the entire energy, you can also should also be very closely represent the average wave energy, that is right. Okay. Now if the area of the area under the histogram curve is known, one can directly get the H bar or HRMS etc. Using the Rayleigh distribution formula, and we can also determine from this the probability of occurrence of different wave heights. That is what I have been explaining here. So next, one is the probability density, the other thing is that if I want a wave height, the probability of wave height greater than a specific value. So what you get from this is a wave height less than or equal to a specific value. Now very often you will be talking in what is known as probability of exceedance. Probability of exceedance is nothing but what is the probability of wave height greater than a specific value. In this case, in this example, what is the probability of wave height greater than 1.5 meters. So as long as that probability of exceedance is less, then the percentage of risk involved in carrying out your operation with the limited conditions of your vessel is what? If the probability of exceedance is very less, probability of exceedance is very less means you are safe. So this kind of information can be obtained from this kind of analysis. So if HI is 3 meters and HRMS equal to so much, I get this probability of exceedance equal to use the equations, you get the probability of exceedance as equal to 0.05. What does that mean? HI is equal to 3 meters and the probability of exceedance is 0.05. So that means there is a possibility or probability of 0.05 or 5%. that the wave height will be greater than 3 meters. So in offshore operation 5% risk is not much, you can easily digest. So this kind of information can be obtained from the probability of exceedance. In other words, out of a number of waves n into that value exponential of minus hi square divided by HRMS square will be higher than hi. So when you have this kind of a formulation, it is very easy for us to calculate the other wave characteristics like your h mean or h 1/3 or h 110 etc. So is there any question? So if we say that of a site the wave height follows a Rayleigh distribution, it was Longitude-Higgins who did a considerable amount of work in this area, where he tried to prove or he tried to see how the waves follow the Rayleigh distribution, and also try to establish some relationship between the different kinds of wave characteristics. For example, h 110 is equal to 1.27 into h 1/3, that is equal to 2.2 twice, almost twice the mean wave height, as you can see here, or the significant wave height is approximately 1.6 times the average wave height. Or you have the other kinds of variations, relationship like h bar, that is the mean wave height is 0.9, approximately 0.9 times the HRMS, and the significant wave height is 1.4 times HRMS, and then all these values are in terms of HRMS. So I have just given a small comment here from Longitude-Higgins. This is what it says, that these results represent the mean values of wave records taken together. So individual wave records containing less than 100 waves may give noticeable departures from these mean relationship. This I have already indicated in the earlier lecture, wherein I said that when you want to analyze a wave record, you should have a minimum of 100 waves. So all the above relationship are valid for a narrow band spectrum. So usually when what do you mean by a narrow band spectrum? Narrow band spectrum looks like this, and a broad band spectrum may be looking like this. That is, here energy is concentrated within narrow band frequencies, whereas here energy is spread over a wide range of frequencies. So from a given wave elevation, if you say that it is a narrow band spectrum, it usually it will follow the eta will follow a Gaussian distribution, and wave height will follow a Rayleigh distribution. Okay. If eta is a narrow band process, it will follow Gaussian process, or if the wave elevation follows a Gaussian, it is vice versa. And then you can also say that it follows you can see that it follows a Rayleigh distribution. The general guideline, whether it is a narrow band or broad band, if it is anywhere between epsilon, that is the spectral width parameter is less than 0.6, I would say, then we say that it should be expected that the wave elevation follows a narrow band spectrum. So, all these above relationships of the different wave characteristics have been obtained by Longitude-Higgins on the assumption that it is a narrow band process. But the wave elevation need not have to follow always the narrow band spectrum. So, in case you come across waves that are following a broadband spectrum, then you need to have some kind of a correction factor, and this correction factor was introduced by Cartwright and Longitude-Higgins, and that is suggested by multiplying, you multiply all these values by a correction factor which is 1 minus epsilon square. Epsilon is the spectral width parameter and the whole thing is half, I mean the square root of 1 minus epsilon square. So, this correction factor has to be used, and your spectral width parameter here I have provided the relationship with your crust period and the zero crossing period. So, which can be obtained using the spectral moments or by the statistical method. Here in when you are talking about random process etc., it is always better to use the spectral method, but there is no harm in using the statistical method. So, we have obtained, we have seen the different wave characteristics. Now, what is that we will do next? Next again we will try to see if we are able to compute the wave characteristics and compare with that of the predicted formula, that is the formulas which we have given. So, we are taking the same I mean the data, and the values are the same as we have seen in the problem, and now for which we have calculated h bar as equal to 1.45 meters. .45 meters, this is easily obtained. Next is we use the Rayleigh distribution. Rayleigh distribution says what? Rayleigh distribution says this is equal to 0.89 into HRMS square. But the same problem we have calculated earlier, and this HRMS square, HRMS is 1.73. It is HRMS. So, if I calculate my I mean h bar from this, I get 1.54 using this relationship, because since I have already calculated my HRMS, this is going to be about 1.54 meters. But by the usual calculation you get the h bar as 1.45 meters, that is the order of difference. Okay. So, it is seen that the Rayleigh distribution fits well in general the wave data in general, because but there are some conditions like your narrow band process etc., which I have already explained. So, if it follows a Rayleigh distribution, we say that H max is approximately equal to this is actually given by Goda in his beautiful book on random waves. So, I would strongly suggest for the students to go through the book written by Random Seas on maritime structure. I think the reference is given at the end of the text. So, that will give you all kinds of information including this Rayleigh distribution etc. Then so, this H max can be safely taken as, so you see that H max divided by H 1/3 should always be less than 2. For an ideal C state, or in general you say that if H max by H 1/3, not if you say it has to be mostly less than 2. Very rarely it exceeds 2, very rarely, and in the event it exceeds, then the waves are called as freak waves. Freak waves. So these freak waves has a lot of energy, and they can really lead to some devastating effects, and existence of freak waves have been proved in several coasts, particularly in the North Sea and several other seas. So you need to look for the word freak waves over the net if you want to have further information on this topic. It is quite interesting on about these freak waves. So in the design of offshore structures, usually H max is taken as twice the H 1/3, or slightly a higher value is often employed, and this depends on location sometimes. So for example, in locations where you have where it has been proved the existence of freak waves has been proved, then they have to go in for a value higher than 2. For the design of breakwaters, Goda suggested that the H max can be 1.8 to the 1.8 times the significant wave height. Is that clear? So we have seen the statistical method, we have seen the spectral method, and in the statistical method what we have seen is the following of whether the wave heights follow a normal distribution, whether the wave elevation follows a normal distribution or the wave height follows a Rayleigh distribution, and in what way it is useful to the field, etc. All these things have been discussed. Now we will get back to the spectrum in order to understand more about spectrum. So initially we started with statistical analysis. We tried to understand all the different methods of statistical analysis. Then we took up some examples and found out its usefulness in the field. The same way we will try to repeat for spectrum. There are two types. In the case of, we have been dealing with, I have already shown that the spectrum looks a single, mostly the spectrum, I have already indicated what is a spectrum, etc. Usually the spectrum is a single peaked spectrum. The energy is concentrated around a single frequency, the peak energy. Now there are two types of double peaked spectrum. You can have multiple peaks or double peaked. So broadly there are two types of spectrum. One is the wind dominated spectrum and the swell dominated spectrum. The wind dominated spectrum could have been generated by a low frequency swell system. That is, low frequency swell means swell is outside the first area. Please recollect my lectures on the generation of ocean waves. So could have been generated by a low frequency swell system that had travelled a considerable distance, losing much energy before meeting a wind wave system. So under the wind wave system, the energy between the wind, energy from the wind is being transferred to the growth of waves. The other one is the swell is already left the fetch, the fetch area. Spectra dominated by low frequency low frequency components could have been generated by a refreshing wind or by a change in the wind direction. which creates a system of short period waves coexistence with a old wave system. So now when the wind does not drive the old system longer, the wave components become uncoupled and the wave system turns into a swell. So when you have a swell dominated spectrum, you can see it like this. When you draw the spectrum for a given location, and if you have a spectrum on the left hand side similar to what you have on the left hand side, then you have a low frequency component from the, I mean the energy from the low frequency component is less, and then in that case you see that this is dominated by the winds. But whereas if you have a low frequency component dominating the wave, I mean the spectralistic curve, then it is called as the swell dominated spectrum. So when you do the analysis you may have something like this. There can be some tidal component also included in your spectrum. You can also separate the tidal component from the, so when you say tidal component is only within the low frequency, very low frequency you can have a very long period. When I say low frequency, it is a very long period which is included in the wave elevation which you have already measured. So this kind of information can be obtained, the frequency component, the energy contribution from different frequency bands, etc., which I have already told in my earlier lecture. Next, unfortunately this is what is called as your Beaufort scale. So normally when you have a cyclone, you get an announcement in the radio or in the TV saying that wind speed of so much kilometers per hour, we have a low pressure area of Bay of Bengal, and this is going to be associated with some wind speeds of varying some values. Flag number say 6, flag number 7 is hoisted in harbors. I am sure some of you must have heard. What is this flag number? Flag number is nothing but the Beaufort scale, that is the number is given for the wind speed in terms of wind speed and in terms of the wave height. So for example, it is when it is 0, then you do not have any number, that is going to be 0 because it is calm. Then when we have about 2, then we say it is light breeze, whereas wherein you have the wave height of approximately 0.2 to 0.5 meters, and you have the description of the sea condition and the wind condition here, and so you have other values like gentle breeze, etc. So for example, if you have high wind and moderate gale, etc., so you see that the wave height in this case, if the Beaufort scale is 7, the wave height is of the order of 4.4 to 5.5 meters, and if you as you go down you see that 12, let us see the 12, that is during a hurricane. So you can have a wave height of the order of about 14 meters. So this Beaufort scale gives you the conditions of the marine environment in terms of your wave climate. So this is quite important that you have this Beaufort scale, and you can also refer to the net for much more details on the Beaufort scale. So as we had earlier about the standard distributions like your Rayleigh distribution, you now have to go in for standard representation of the spectra. What does that mean? Is the purpose is same, similar to what you did with the Rayleigh distribution, that is in the statistical domain. Now you are going to do it in the spectral domain. Why do you need this? First of all, why do you need the standardization of standard representation of spectra? See, for example, if you want to I will just take a few minutes before we go into the details. Suppose if so naturally the spectra, as I have told you, varies like this, that is spectrum, spectral density, and the standard spectrum, maybe I will come to the standard spectrum, the list of standard spectrum later, but the standard spectrum if you plot may be going like this, if in the event it is following. So now here this dotted line is your standard spectrum and this is going to be your measured spectrum. For example, you have proved that the wave elevation of east coast of India follows a given spectrum, let me call it as Scott spectrum. So this is a particular name, like Rayleigh distribution, we have Scott spectrum and we have many other spectrum. So for the time being you assume that someone has already proved that of east coast it follows, it is only an assumption that it follows Scott spectrum. And I have there is going to be some experiment, I mean some offshore development which requires some special kind of a structure to be installed, and before installing maybe it is a floating structure, and when you have a floating structure you know what will happen when it is moved. So it will undergo motions and these motions will definitely be a function of frequencies. So the motion response of this structure will depend on the input spectrum. So I want to find out the response of this structure for different frequencies. I need to do that, because for some frequencies this mooring can go to the last to the extreme end. So and I also need to find out how high it moves, how transfer direction moves, all this information we need. Then we try to say that if someone has already said that it follows a standard spectrum like the Scott spectrum, I can simulate the Scott spectrum in the field in the lab. So this variation of the wave elevation in front of the structure can be simulated in the flume, and the motion response of this structure can be adopted. Of course you need to use a model scale for all these things. At least, so this once you have a standard spectrum that permits us to easily handle the problem, because you are standardizing all these results, the presentation is also quite easy, straightforward. And once you know that this is a theoretical distribution, then it becomes very handy in order to show how the whole response function can look like. So is that clear? So that is the reason why we have a standard spectrum similar to a standard probability distribution curve. So a number of mathematical spectral models have been proposed by researchers in the past. These have been tested with the measured elevations and are generally a function of significant wave height or peak period. So you have and or peak period. So you see that the spectral density will be a function of Hs or a function of Tp. Tp is, this is peak f naught and Tp is 1 by f naught, that is the frequency of maximum energy, or sometimes it can be Tp and Hs. So here in this case we call it as single parameter spectrum. The second one also is a single parameter spectrum, and the later you can also have 2 parameter spectrum and multi parameter spectrum, which we will see later. So later the shape factors have been introduced, because initially we had only these two, then later the shape factors were used and introduced to fit in order to fit the measured spectrum, because if this is a theoretical spectrum and maybe it is something like this, the measured spectrum, then we use a third parameter. The third parameter was tried so as to pull this peak towards the measured data, and that is what happened in coming up with what is called as a John-Swap spectra, which we will be discussing later in the next later. Okay. The most widely adopted single parameter spectrum is the Pearson-Moskowitz spectrum that was done in 64 based on the significant wave height, or it can be described by the wind speed alone. So we will just have a look at it later.